Hi, everyone, and welcome to our usual ITMP Wednesday seminar. And today we are delighted to have Dr. Donal from the University of Edinburgh, who will speak about amplitudes for Hawking radiation. So the talk is 1 hour, but you're free to extend it if needed.
Okay, great. Thank you. Okay, I guess I'll start then. Yeah, well, first of all, thank you for the invitation. It's a pleasure to have the opportunity to uh, discuss my work with everybody. Um, what I'm here to tell you about is some work I've been doing connecting Hawking radiation to scattering amplitudes. So firstly, let me say who the work is with. So I've been working with a student, with a postdoc, I should say, Raphael Aude, as a postdoc with us in Edinburgh. And also Matteo Sergala, who is currently a postdoc in IPHD in Paris. Matteo will soon be moving to UCLA. I want to start with a little bit of motivation, just to put this work into context, because really what I'm trying to do here is to build links between various fields. So let me just tell you where I'm coming from and why I think that there's something interesting that can happen. Now, I've been doing some work over the last several years with many colleagues on this business of applying scattering amplitudes or methods of scattering amplitudes to classical gravitational waveforms. And we have a formula, which I'll explain in more detail, schematically shown here, for the waveform. So this is the gravitational waveform in a certain process. And it's given as an integral over effectively an amplitude. Now, this amplitude here, a little vague about it. I'll explain it in more detail later in the talk. But this amplitude, the way I think about it is it's the amplitude for single graviton production during this process. It's not quite a standard amplitude because the boundary conditions are different from the standard in-out boundary conditions. This is more of an in amplitude, but as we see, it's very closely connected to an amplitude. You know, at some level of intuition to begin with, we can just think of it as being an amplitude. There's one additional term here in the dots. Again, I'll explain a little bit more about that, but it's also some kind of amplitude, really a product of amplitudes. In any event, we can write the classical waveform as a certain integral over scattering amplitudes. But that's a little bit funny, right? Because scattering amplitudes are objects in quantum field theory, they're quantum mechanical objects. So we have to do some work in using this formula to remove the quantum mechanics so that we're talking about something classical. But you might then think maybe there's something interesting in the quantum stuff that we're removing. Maybe there's other gravitational physics, which is quantum mechanical, that we can access with these methods. And the obvious, process to then think about is pair production, and in particular, the production of Hawking pairs in some black hole process. Now, firstly, you might well be very puzzled at the outset because obviously, I'm talking about single graviton production amplitudes, but the gravitational field, like the expectation value of the gravitational field operator on graviton number states must always vanish. So it can't be, it's not like one graviton is giving you the gravitational wave, right? So that, intuition is captured by the fact that the expectation value of the metric operator, so H here is the perturbative quantum gravitational operator. The expectation value of the quantum field on any number state, so n is a graviton number state, must always vanish. And that's so because H has a term which, has an annihilation operator. The annihilation operator acting on the number state is obviously going to lower that number. So this overlap would then be zero. There's another term where the H has an A dagger, a creation operator. But again, if I create a particle, then the overlap is going to vanish. So you might then think, gosh, what am I talking about? This guy, there's single graviton production amplitude. Clearly, single gravitons aren't gravitational waves. And the resolution of that is that the actual final state in this process, if I take S and act in some initial state to compute the final state, this must be some sort of coherent state. So the gravitons all exponentiate into a coherent state. The coherent state obviously does have an expectation value on the gravitational field operator. And what's exponentiating are these single graviton production amplitudes. the intuition here is that each graviton in the gravitational wave is produced independently of one another. And the parameter of the coherent state then is just the information about single graviton emission. And this expectation value then effectively just differentiates this coherent state, brings down the parameter, which is this single graviton production amplitude. And that's why you can get all of the information you need to discuss this classical gravitational wave by studying a single graviton process. So there's some exponentiation at the heart of this. So each graviton is produced independently, and that exponentiates. So that's the situation in this classical regime. We have exponentiation of single graviton production into a coherent state. Now, it can happen under certain circumstances that there is a correction, a first quantum correction to this sort of formula, which is something like this. So now there is a factor in the final state, which involves the correlated production of pairs of gravitons. This is called a squeeze state in quantum optics. It's a quantum mechanical state. But the physics here is that pairs are produced correlated with one another, but each pair is produced separately. But those are uncorrelated. And we know this is known to be the situation when you have Hawking radiation. So Hawking radiation, the final state is always a squeeze state of this form. So it's very similar, you see, again, to the gravitational waveform. The gravitational waveform, we have just this exponentiation, single particle production. In the Hawking radiation, there's an exponentiation of these pairs. If you want to understand the Hawking process, all you need to do is understand this pair production amplitude. Okay, so that's sort of the idea, that the mechanism behind pair production is very similar to the mechanism behind the successful application of amplitudes to classical gravitational waves. So what I want to present to you is, a version of Hawking's calculation, essentially, but cast in the language of scattering amplitudes, expressed as closely as possible to the ways we've been using to understand gravitational waves to date. I'm hoping then that we can use this in the future to go beyond that. So in particular, in the context of gravitational waveforms, we understand quite a lot of interesting physics. For example, there's the interesting physics of back reaction, so the radiation reaction. So this is one of the diagrams that's relevant in that computation. So it's just this diagram actually. It's interesting in electrodynamics. This diagram is very closely connected to the Abraham-Lorentz-Dirac radiation reaction force. But it will be interesting then to try and compute the back reaction to emission of a Hawking pair. So to understand the back reaction, actual controlled computation, the back reaction of the Hawking radiation of the system. I think that's an achievable goal in the future. Okay, so that's my motivation. What I then want to explain in the rest of the talk is, well, in the first part, I'll discuss more about this classical situation, the classical waveform, and their connection to amplitudes, really these slightly generalized amplitudes. So I'll put a little bit more meat on the bones of these formulae I was describing for the waveform in terms of amplitudes. So that will all be in the context of classical gravitational waves, but in the second part of my talk, I'll start moving on towards the case I want to discuss today, the Hawking radiation. And I'll begin by connecting amplitudes to Bogoliubov coefficients. So obviously, these Bogoliubov coefficients have been very successful in their application to Hawking radiation in the past, how Hawking worked himself in his original paper. So I'll explain how these things are connected, these Bogoliubov coefficients are connected to amplitudes. And then in the third part, I'll describe some details. So I'll recover the Hawking spectrum basically by summing a bunch of diagrams. That's sort of the heart of what I want to tell you about. And then I'll finish with some remarks about things we might do in the future, or directions I'm interested in next. Okay, so now in this first major part of the talk, what I want to do is describe just this setup of computing waveforms in classical gravitational situations. Now, the situation that is simplest to discuss is a scattering encounter between two black holes. So these diagrams here are supposed to be pictures of some kind of a black hole. They're separated in the past by some impact parameter b. I'm going to scatter them at one another. Now, in that case, the waveform, rather than being the sort of chirp we're familiar with from LIGO, is a bit of a bump. So it's a bang, most radiation emitted when the particles are close together. This waveform is computed in terms of an amplitude by a formula like this. So there's an integral to be done, and the quantity here is well, rather than being a normal amplitude, which would just have an S matrix, a single S matrix, it's a generalized amplitude because there's two F matrices here. Now, I'll spend some more time discussing the connection of this to the usual amplitudes in a moment. But the point here is essentially the boundary conditions are a little bit different. That's why there's different two S matrices. Another just a comment about the physics here. I'm going to work in a situation where I'm thinking of the black holes as being just classical point particles. So really point-like objects. So I'm not taking into account finite size effects of black holes, in particular phenomena like the ability of the black hole to absorb some energy and change its mass. Such effects only occur at very high orders in perturbation theory. They're well beyond any perturbative order that's been computed to date. So it's sufficient to think about these things as being point-like particles. Of course, for LIGO physics, one would want to connect this to bound states. It's a very interesting story, but not what I'm going to talk about today. Okay, now, first a general comment about why amplitudes come into this picture. It'll be the same for the Hooking situation. And it really just arises from time evolution. Now, I'm always working in the interaction picture here. So I will start in the far past with an initial state, some state psi. I'll describe that in more detail in a moment. I then time evolve this into the future with the all-time evolution operator, this unitary operator from time minus infinity to time plus infinity. But that unitary operator is what we call the S matrix. Writing the S matrix as 1 plus IT, then the matrix elements of T, the transition operator, are the amplitudes. So you see, the amplitude is just necessarily going to come into this problem because I have time evolution from some simple state in the past, those two particles, and some more complicated state in the future. Now, since I want to use scattering amplitudes to describe gravitational waveforms, I first of all have to express gravitational waveforms in some sort of quantum field theoretic language. And the way I do that is by thinking of the measurement as being a measurement of an expectation value of an operator. The operator is the Riemann curvature operator. So this here, this R is just that Riemann curvature operator. There's some dots here because there are indices, mu, nu, rho, and sigma. There are some indices, but they won't really be important because I'm always going to pull off the dominant curvature component at large distances. So that's the curvature component that is, a 1 over R distance factor. I'm only going to look at the 1 over R distance factor. There will be other terms in principle in the curvature, which will be suppressed by 1 over distance squared, 1 over distance cubed, etc. But, bearing in mind that I'm thinking of a situation like LIGO physics, where you have, astrophysical distance between your source and an observer, well, then 1 over that distance squared is completely unobservable. So for all intents and purposes, it's really just 0. So it's sufficient to restrict to that leading term, the 1 over distance term. That's what LIGO measures. So technically speaking, I'm talking about the leading component of psi4, the Newman-Penrose psi4. That's just a curvature component. Now, the initial state, so I need to put in some initial state corresponding to my two particles. And I want to have some initial state which is in the domain of validity of the classical approximation to the quantum field theory. So I will start by taking two particles in plane wave states. Now, these two black holes will be made out of these two quanta. They will be quanta of completely different quantum fields with completely different masses, right? So two totally different objects, these black holes. I want to localize these black holes sufficiently well in both position and momentum. So rather than having just a plane wave state, I introduce some integral over wave packets. So the wave packets are just these Gaussians here. So I think about some Gaussian function that I'm integrating over. And the job of those wave packets is, as I said, to do this localization. I've also introduced a translation operator here to translate one particle with respect to another. So that's through the impact parameter P. Now, this state, as I said, it should be in the domain of validity of the classical approximation to the quantum field. So that will be the case if the uncertainty in these wave packets is negligible compared to scales which are large and which I keep, the important scales in the problem. So for example, thinking about these wave packets in position space, well, then they will have some spread. So there will be some wave packet spread, say some distance L of which the Gaussian, has support. If that distance L is very small compared to the impact parameter B, and I expand in the quantity B over L and neglect, I'm expanding in L over B. L over B is a small thing. L is the uncertainty, B is the big thing. So I expand all my observables and powers of L over B and neglect anything that's order L over B, so I just keep the dominant term. Well, then my particles will be treated as being point-like. Similarly, if you Fourier transform this wave packet, there will be some uncertainty momentum space. It'll be of order h bar over L. So if that uncertainty momentum space is small compared to, say, the classical mass of the particle, and again, I expand in that uncertainty over mass and throw away this uncertainty terms, well, then I will have removed all of the quantum uncertainty from my problem. So this is sort of in the spirit of effective field theory here. I'm always going to be doing some sort of expansion and neglecting quantity suppressed by some dimensionless variables. So that's the way we organize a classical initial condition. The final state then is obtained by acting on the classical initial conditions by the S matrix, and that will take care of all of the dynamics. So once I've arranged these initial conditions so that the whole problem is going to be in the domain of validity, the classical approximation, well, then I'm good. This expectation value will recover the classical value when I do all of these expansions and neglect the subleading term. Okay, so another point about this, of course, is since all of the time development is coming from the S matrix, I'm guaranteed to get expressions in terms of amplitudes. Okay, so now just to go into this in a little bit more detail, let's take that Riemann curvature operator and write it in terms of the quantum field. So H here again is the metric metric perturbation of the quantum field. Now, since I'm working to leading order and distance, we get to radically simplify the expression for the Riemann curvature. And that's because each of these h's in its expectation value is going to have a 1 over distance factor. So the terms of the Riemann curvature, which have h squared, will have a 1 over distance squared. The h cubes will have 1 over distance cubes, etc. And I get to ignore all of those. So I truncate the Riemann curvature tensor in its perturbative expression of leading order in H. So in other words, it's just the linearized Riemann curvature tensor. So that's a great simplification, that we get to simplify the meaning of the curvature here. So again, that's sort of why there's some dots. I mean, there's always going to be some index permutations here for the H and the derivative here. Now, writing H, as we do in quantum field theory, in terms of an integral over momentum space with some creation and annihilation operators, the derivatives then are going to act on the exponential factor, the Fourier transform factor in that expression, and bring down powers of momentum. So the k's in this expression, so this is just the way forming out, trying to get into more detail. The k's are just emerging from these derivatives in Fourier space. The two epsilons here, that's just the polarization tensor of the graviton. I've written that tensor as an outer product of two polarization vectors. That's always possible. So the two epsilons, just the graviton polarization. The measure here, d5k, is just an integral over the on-shell phase space of graviton. That's d4k, there's a delta function setting k squared to be on-shell, a theta function for positive energy. And then everything else is just what was in the previous expression for the expectation value. So the initial state, the S and S dagger, and I've just written the annihilation operator from the quantum field. There's another term involving the creation operator, the complex quantum field. Okay, now that formula, well, in terms of quantum field theory, the key object is just this expectation. So this expectation here involves my states. Now I'm writing those states in terms of some wave functions. These are just the psi's. I'll have that translation operator, etc. in them. And then, really just something we can compute in field theory. So some overlap, some bracket with well, what look like two initial and two final particles are all, of course, coming from the initial expectation value. So P1 and P2 in the ket, and a P1 prime and a P2 prime in the bra, and then again the S dagger A of KS. So that's the actual thing that we need to compute. That's this generalized amplitude. Now, this generalized amplitude is very closely connected to amplitudes. One easy way of seeing this is write S as 1 plus IT. Now, the annihilation operator here is a graviton annihilation operator, But I didn't put any gravitons in the initial state. So the initial state is made up of quanta of these scalar fields corresponding to the black holes. So that annihilation operator, if it hits this state, will give me nothing. It'll vanish. So we get to replace this S with T, IT. This S dagger, in the meanwhile, there will be two terms, a 1 plus 1 minus IT dagger. So the term where I extract the unity from this S matrix is just this term here. The term where we have both the T dagger and T is the second term here. Now the first term, that's just an ordinary 5-point amplitude. A matrix element of T between number states. So it's a 2 to 3 amplitude, a 5-point amplitude. A loop amplitude, there's nothing here to stop you, to force you to be working at tree level. So this is some loop amplitude one has to compute. And the second term, well, by inserting a complete set of states between, maybe that A and this T dagger, we can rewrite this thing as a cut, or as a product, like an integrated product of two amplitudes. So think about it as being a cut of a 5-point amplitude, or as being an integrated product of two amplitudes. So this is, there'll be various terms in here. There can be more than one particle. This particular diagram is just one. There can be intermediate particles in that cut as well. Yeah. But the summary of this situation is this generalized amplitude can be computed from amplitudes and cuts of amplitudes. Now, this business, that it's not an amplitude but a generalized amplitude is important. But in some respects, the difference between the amplitude and the generalized amplitude is very small. So, for example, at next to leading order in this waveform, the only difference between the amplitude and the generalized amplitude is this sign. So here I've written the imaginary part, or just the cuts. So I've written amplitude as something without cuts and something with cuts, the generalized amplitude. So these are all of the cuts that contribute. The only difference for both the amplitude and the generalized amplitude. If I were to talk about the amplitude, I'd have a plus sign. What this subtraction term does in that previous formula is just flip the sign of this term. That's all. Now, it's interesting, though, to understand these things in a little bit more detail. And here I'm going to begin to build up some formalism that I'll use to talk about Hawking radiation. So let me introduce notation for the initial Hilbert space and the final Hilbert space, so the in and out spaces. I'll have ladder operators in the initial Hilbert space, A and A dagger, and another set of ladder operators for the final Hilbert space, B and B dagger. Excuse me. Since the S matrix relates the in and out states, it follows that the B annihilation operator is given by S dagger A of S. Now, in these terms, an ordinary 5-point amplitude involves creating some particles in the past and annihilating particles in the future. So I've written a 5-point example here. You create two particles in the past, so they're created with the ladder operator of the in state and annihilated with the final state ladder operator. And we could also just introduce an S matrix here. And that would be, then I would have, all A's, an S, and two A daggers. The generalized amplitude is different because you create and annihilate particles, if you want in the past, and annihilate only one particle in the future. So there's one B in the middle, there's the A daggers corresponding to the ket, and the A's corresponding to the bra. And this arises, again, because I had an expectation value. So the physics here, the physical difference is that there's some different I epsilons in the Feynman, the Feynman I epsilon prescription is different. That reflects the fact, that in this expectation value, I set up a problem corresponding to a classical physics problem where you'd use retarded propagators anyway. So maybe not so surprising that there's a different I epsilon in the propagators. So in other words, this thing, our usual amplitudes are in out. This thing is in. So it's in here. It's connected then to to this Schwinger-Keldysh approach to quantum field theory, where you have a closed time path. So you can think of these A's as being the beginning and the end of that closed time path, and the B as being the middle where you turn around. It's interesting that this E, this generalized amplitude, sometimes we call it expectation and CE, but this thing admits a classical limit, whereas the amplitudes don't. Now, what I mean by that is, I explained that I was going to perform some expansion in dimensionless quantities, these uncertainties, the wave packet size over impact parameter and things like that. But it's very important that the dominant term, is of order 0 in those expansions. If you just look at the amplitude, that's not what happens. So it looks singular in this limit. But the expectation value, everything works as you'd expect. Okay. Now, again, just to take a little bit of a step towards the situation for Hawking radiation, I could just as easily talk about scattering on a background. I'm going to use the background for the Hawking radiation. So if I scatter a light black hole off a heavy black hole, a little like this, then the waveform will be given by a related but different object. It'll be a 3-point amplitude on the background. So here now the background would correspond to this black hole that I'm keeping static, thinking of it as being very heavy. This amplitude there will correspond to creating the light black hole and then measuring gravitons emitted from this process. So generalized 3-point amplitude on a particular background. And that would be appropriate if you're interested in performing a calculation of leading order in the mass ratio. So the mass of the small black hole over the large black hole. This is relevant for LISA physics, like extreme mass ratio and spirals about a small black hole around a supermassive black hole. People are interested in this, very interesting physics. Okay, so that's sort of where I'm coming from. I've been working on this story, these classical gravitational waveforms for a while. But now, well, maybe it's interesting to consider quantum corrections. So let me start moving on to talk about, the actual physics of Hawking radiation I want to focus on for the rest of the talk. Firstly, I'm going to simplify my life a little bit. So I referred to production of graviton pairs in my introduction. That's partially because when we are thinking about gravitational waveforms, of course, we are interested in the production of single gravitons. But in Hawking radiation, you can be interested in graviton pair production, but it's also perfectly interesting to consider scalar, the production of scalar pairs. That's a little easier. It's not a big deal. I can certainly talk about the production of gravitons, but I'll follow, a well-trodden path here and speak about the production of scalar pairs and the rest of this talk. Now, I'm also going to work in a particular background. So the background will be a radial background corresponding to a black hole forming in a collapse process. The metric is given here. So this is an exact form. It's a Kerr-Schild metric. So the Kerr-Schild vector is given by this k mu here. So k dot dx mu is just dt plus dr. It's an old vector so that this metric is exact even if it's truncated at linear order. Now, if the theta function weren't here, if that was just unity, this would be an expression for the Schwarzschild metric in Kerr-Schild coordinates, an exact expression for the Schwarzschild metric. Obviously, with the theta function here, well, that means, when the theta function in, when t plus r is negative, the theta is 0, and the metric is flat. When t plus r is positive, and the theta function is 1, the metric is curved. It's some kind of a Schwarzschild. So corresponding to this theta function, there must be something happening to source, to build up the black hole. So some matter collapsing to build up the black hole. And that matter is, in this approximation, a very thin shell of radiation falling into the origin. That's why there's this sort of discontinuous theta function. It's because I'm working in an approximation that the shell of radiation is very thin. Now here's a picture. Now this is a picture in sort of Eddington-Finkelstein style coordinates. The arrow here is supposed to be the t plus r axis, which you see here. Vertically I have time and horizontally some radial coordinate. Now, in the far past, then there's a flat region where the theta function is 0. In the future, there's a Schwarzschild region and a black hole region, right? The red line here is that shell of infalling radiation where the theta function is transitioning. It's maybe worth mentioning that the event horizon is given by this blue line, and the event horizon dips into the flat region. And that's just because if you're an observer here, in the 3D flat space, it's behind the event horizon because as soon as the radiation passes you by, you realize, oh dear, no, I'm stuck. I'm already in the black hole. So this is this teleological property of the event horizon forming, a little bit before, the physics that creates the black hole. Okay, so that's going to be the picture of this background. I'll come back to it. We need to talk about this in various places. But what I want to do now is really begin to talk about the Bogoliubov coefficients and what they have to do with scattering amplitudes. So I'll consider in this background a scalar field. So the quanta of these scalar fields are going to be the guys that are being produced. So this pair production diagram will be quanta of these scalar fields phi. The action for the scalar field then is given by this quantum field, times g mu nu. But g mu nu, well, root g is 1 in these coordinates. H mu nu is just, here. So that's the classical perturbation on the previous slide. So just this term T2gm with the theta function, 1 over r and k mu k. Okay, now the Bogoliubov approach again is very useful, and it's expressed in terms of the relation between the ladder operators in the past and in the future. So this is just the same setup as I discussed a few moments ago. A and A dagger are ladder operators for the in-Hilbert space. B and B dagger are the operators for the out-Hilbert space. Now, in this case, the equation of motion for the quantum field is very simple, and that leads to a powerful approach. So the equation of motion is a second order, homogeneous linear partial differential equation. So we can solve this differential equation, at least in principle, by imposing some boundary conditions. So let me first of all find a basis of solutions, which I'll call the past solutions P for past. Now the boundary condition on these past solutions is that as time goes to minus infinity, the waves become e to the minus I p dot x. Right? So in the past, these terms cancels off, so I'm just solving a free wave equation. So this will be a perfectly acceptable basis of solutions in the past. Notice that the basis is labeled by the momentum of the particles in the past, where the waves are free. Now we can express the quantum field on that basis in the following way. So just an integral over these momenta, because they labeled the free guys in the past. The basis functions themselves, the capital P's, and then ladder operators. Now the ladder operators that are relevant here will be the A's and A daggers, the ladder operators for the in-Hilbert space, because in the very far past, the wave functions here are free plane waves. Okay, that's one basis of solutions. There's an obvious other basis of solutions which we could think about, the future solutions. So I'll call these guys F, F for future. These future solutions have the property, the boundary condition which we impose, that as time goes to plus infinity, the waves are free, e to the I p dot x. Again, in the far future, this term falls off, so we can neglect it, and we're solving a free wave equation. So, so the solutions are these modes F. I can then express the quantum field again on this basis. So they're labeled by the momentum of the particles down the far future, and the appropriate, I've got the basis of solutions, the wave functions, and then the appropriate ladder operators will be the ladder operators in the future, because this F is the boundary condition that corresponds to free waves in the far future. Okay, so we have two expressions for the quantum field, these two here. But of course, there's only one quantum field, so these two expressions are equal. And it's this equality that leads to the power of the Bogoliubov approach. Now, you can basically see by eye that this is going to mean that there's some relationship between the A's and the B daggers somehow involving these F's and P's. So to understand that relationship in more detail, let's suppose I write the P solutions on another basis, on the F basis, right? F is a basis, so I can write the P solutions on this F basis. Since P is a complex solution of the wave equation, we need F and its complex conjugate, F and F bar. These A's and B daggers B bar, I've just written them. They're the expansion coefficients of P on the F basis. But now if I insert this expression for P in the quantum field and gather the coefficient of F, well, the coefficient of F, we see it must be B. So the B annihilation operator is the coefficient of F. So in other words, well, you can see by I, there's going to be a capital A times a little a coefficient of F. But also because of the Hermitian conjugate here, I'm going to have to take the complex conjugate of this term. So we'll get a capital B times a dagger. Right? So in other words, we'll have an expression like this. The B operator is given in terms of this A, this is the Bogoliubov A, times the annihilation operator, and the Bogoliubov B times the creation operator. So this is the powerful expression for the Bogoliubov coefficients. Of course, it's always the case that B is S dagger AS. That's always true. So it's just this additional relation that's so useful. The Bogoliubov coefficient, well, just from this observation, you can write the Bogoliubov coefficients as generalized amplitudes, very similar to the amplitude, the generalized amplitudes in the original part of the talk. So to see that, well, I mean, what you do is just exploit, the fact that, I introduce a vacuum omega in the far past, so it's annihilated by the A's. And I guess one way to think about this, if I multiply in from this direction by an A dagger and an omega, so in on this side and on the other side by just an omega, well, then I'm going to pull off the A, right? Because this A will hit the A dagger. I can just compute them through one another. So I'll just get this Bogoliubov A. Thinking now of this thing, I have an omega times an S dagger A of KS. That's these things times the A dagger I multiplied in on the other side here and an omega. Right? So this gives you this A as a generalized amplitude. So it has an S dagger and an A and an S. It's a slightly different one from the ones before, but it's very similar. Similarly, the B is given by, as another generalized amplitude. I tend to think of the A as being something like 1-to-1 because you create a particle and you annihilate a particle. This B is something more like 0-to-2 because there are two annihilation operators. But bear in mind that there are, if you want, the different branches of the Schwinger-Keldysh counter. Now, the observable that we usually talk about in the context of Hawking radiation is the expectation value of B dagger B. So using this theory of the Bogoliubov coefficients, I can rewrite B dagger B in terms of S dagger A S, for the B, and then S dagger A dagger S for the B dagger. Just hook these things together, the two S daggers and then our SS dagger in the middle are unity. And now I can rewrite these things using the Bogoliubov expressions. And it's straightforward to see that this expectation value is just given by Bogoliubov B squared, basically. So in other words, if I want to count the number of particles being produced in the Hawking process, the Hawking particle production process, one just needs to compute Bogoliubov B. But there's another simplification which is very convenient from my perspective as somebody thinking about classical scattering processes. And that's a sort of a crossing that follows from a relation between the bases in the future and the past. So essentially, this just follows by taking an inner product, if you want to think about it that way, the Klein-Gordon inner product between the P and F bases. So one can then write the Bogoliubov coefficients. So I've written them here in terms of F's and the P in the far past, where the P's just become plane waves. So this is the expression for A. Notice that the expression for B, which is obtained from the same sort of logic, corresponds to the expression for A, but just by flipping the signs of these exponential factors here. And well, I mean, you can view this as an analytic continuation from, P to minus P, which is very analogous. I guess this is in some way analogous to the usual crossing we do in quantum field theory. This is, it's not the same, but it's analogous. There's some analytic continuation from a momentum vector that drags a particle from the past into the future. Here, the analytic continuation is crossing, again, it drags a one-to-one process, this A, into a 0-to-2 process, the B. So for me, that's fantastic, right? I've spent years computing scattering processes, and now with this logic, we can understand the production, the production statistics of particles in the Hawking process by looking at a plane-out scattering, an in-to-out scattering process. So this is the picture here. So now this crossing allows me to replace the scalar pair production, which we want to talk about, with a very familiar scattering process. Again, now I should say I want to make clear that this is, I'm following Hawking's footsteps here. This is what he does in his original paper. He has a particular scattering process, and from that he deduces the pair production statistics. Okay, so now I'm going to discuss that Hawking scattering process. Now it's a scattering process on this background, this Vega background. So here's the background again. We have this shell of infalling radiation at T plus R equals 0. The event horizon starts at a finite value of T plus R, minus 4 GM. It's a simple calculation to see the minus 4 GM there. Now, I'm going to scatter a particle through this background, following Hawking. I want the particle to come in and get out. So I must scatter it in so it's not behind the event horizon. So we think about some particle which is localized at some advanced time, T plus R equal to some value V, which is less than minus 4 GM, so that the particle can come in and fall in, pass through the origin before the black hole forms, and get out to the future. There's a perturbative parameter in that process, which is the ratio of V over 4 GM. That's important in our thinking about this. So this perturbative parameter, it plays a role very similar to the role essentially of the G Newton in what we call the post-Minkowskian expansion of scattering angles in the classical study of particles scattering, black hole scattering. So something that's well studied using amplitudes, and we have built up a lot of understanding of this process and the details of that computation. And this thing here plays a very similar role. That again helps us organize our thinking. Okay, now I want to understand this process, the scattering process. So, using the methods of amplitude. So Hawking, in his original paper, he solved for the dynamics using geometry, basically the geometry of null geodesics in collapsed geometry. Here, I will sum up a bunch of diagrams and get the same result. The diagrams are essentially the Feynman diagrams for this quantum field in this background. They're Lippmann-Schwinger style diagrams. So I'm just solving this differential equation essentially perturbatively. So there's a Lippmann-Schwinger expansion. There'll be a term with one insertion of phi, a term with two insertions of phi, etc. These terms, well, again, play roles very similar to diagrams we encounter in post-Minkowskian studies in classical gravitational scattering processes. It would be very difficult to perform, to compute the full wave function of a particle moving through this geometry. But again, following Hawking, there's a simplification which is very useful. And that simplification is to take the particle that's falling through as being a high energy particle. So I'm now working in a geometric optics regime. Geometric optics, compared to wave optics, is closely analogous to classical dynamics compared to quantum dynamics. So with amplitudes, we've got good at understanding the passage between classical and quantum dynamics. We can use exactly the same methods to understand the relation between geometric and full wave optics. So this geometric optics approach, it's very like classical dynamics. Again, we can build on a lot of experience. In particular, we understand how this wave function exponentiates. I've indicated a parameter eta here. I'm thinking that when eta is small, this phase oscillates rapidly, and that will lead to the geometric optics regime. On the other hand, this eta is going to play a role very similar to h bar in a quantum mechanical scattering process. So this would be e to the I action over h bar in that case. And then, we understand well that these amplitudes, the amplitude in these diagrams, will have a particular counting in this parameter eta. The tree level diagram is going to come in 1 power and essentially expanding this exponentially. I'm thinking of S as having an expansion in some perturbative quantity. It would be this V over 4gm. But at the same time, counting the powers of this eta. So there will be a dominant term here in this tree diagram. In this next diagram, which, it's a tree-ish here, but, if you think about joining these roundy x's with the line, this will be like a loop amplitude. And since there's a background here, this is kind of like a loop amplitude. So this one loop guy, or similar to one loop guy, is going to have a dominant term, which will have 2 powers of eta, and similar to be dominant terms here, which will have 3 powers of eta. These will all exponentiate. We just need to extract them, check the exponentiation, and then we'll get to phase in the geometric optics region. So now I just have to describe a little bit of the mechanics of the computation. I'll use the notation of scattering amplitudes. So I think of my particle in the past. It's going to scatter through this geometry as being some quantum state. There's some wave packet, some wave packet of momentum space. 5p. It's convenient for me to write this 5p in this form. It's an integral over v, and v is the advanced time here, for a conjugate of the time variable, the energy variable. I am assuming here that phi is only a function of energy. And in doing that, I'm imposing spherical symmetry, so that my particle is really just a wave falling in spherically at the origin. And one reason to do that is because if everything is spherically symmetric, then I will shut off all classical gravitational wave emission. Classical gravitational waves require some sort of a quadrupole. This is spherically symmetric. There's no quadrupole. You'll get no classical wave emission. So the dominant radiation will be this pair protection process. Okay, so the spherical symmetry set is imposed by just choosing this to be a function of energy. As a matter of notation, I find it very useful to think about this EV as being something like P dot B. So P is the momentum of the particle, and I'm thinking of B as just being a 4-vector B0, 0, 0. I'm calling it B because it's kind of like an impact parameter. It's just an impact parameter that separates the particle getting through the origin by some time from when the actual black hole forms. Black hole forms at some time, which are taken to be 0, basically. So my particle just has to get through the origin sufficiently fast before the black hole forms, and then it gets out to scry. Okay, well, the tree diagram involves just one insertion of the interaction action. There are various integrals to be performed, and there was some route we found to performing these integrals, which was convenient. In the end, you find that the diagram, this tree diagram, evaluates in the following way. So there's the integral over this wave packet, the 5v. Here's like that time-like impact parameter, but now the p prime here is supposed to be the energy when the particle is getting out. And there's a factor here, which involves a log of this v. Some parameter mu here, which is absorbing some dimensions. And there is an infrared divergence here, which we've absorbed into this mu. We'll cancel out in the observable. And the rest here is about 4gm, just, obviously the mass and Newton constant and the final energy. Now, as I said, these higher order diagrams should have an iterative structure such that the whole thing exponentiates. We check that happens. So this series, the trivial diagram plus all these higher diagrams indeed exponentiates into this form here. So this is the wave function of this particle in the geometric optics region. Okay, so now that's basically it. That's the key part here. Where we summed up a bunch of Feynman diagrams, and now I'm just going to revert back to essentially following some ideas from Hawking to get the spectrum. So one thing I'm going to do is, it sort of violates my rules. I'm going to delocalize my particle. So I said I will take a particle that's localized at some impact parameter v, at some point, I should say some advanced time v. But it makes the integrals much simpler to delocalize the particle in the past. And if I do that, well, then this object takes the following form. You see that there's just energy factors, wave factors for the energy of the particle. E0 is the energy in the past. There's some normalization, which I'm not going to track here, but there's a definite normalization that flows out of the computation. Now that I've delocalized the thing, we need to worry because, well, part of the reason why I like localizing it was I wanted the particle to come out. But having delocalized, clearly some of the wave function is just going to fall directly into the black hole. So correspondingly, this is not fully inclusive. So the measurement, what I mean by that is that the measurement in the future null infinity, is not a fully inclusive measurement because some of the information about the initial particle is stuck inside the black hole. So correspondingly, we cut off the integral where the log becomes, where there's a branch point. And that's the way in which we're feeding in, and we're very much feeding this in. We're feeding in the information about the event horizon here, saying, well, look, that log goes bad, I'll just cut off the integral. But now this is the formula that you can also see in Hawking's paper. So essentially an amplitude, so I'll call it Hawking's amplitude. And it's the same result as his computation, his exact computation. Okay, so to get the Bogoliubov B, I performed this crossing. It just corresponds to crossing the energy of the initial particle. So this is the avatar. This P goes to minus B crossing. There's just the energy left. We could do the integral. Now, of course, you could do either integral. It doesn't really matter. The crossing just changes the sign of this exponent factor here. But this is the one relevant for counting the number of particles. The integral, as you can see by eye, is basically a gamma function. This exponential just comes out from the change of variables. And now to count the outgoing states, as I said, you essentially compute B squared. It's a beautiful computation, and you find that the result is a factor. Again, we have a definite factor, but the key point is you get the Bose-Einstein distribution from the square of those gamma functions. And the temperature falls out as this. That's Hawking's temperature. So 1 over 8 pi gm. Okay, and that's the basic stuff I wanted to tell you. Let me finish with sort of an outlook for where I'm hoping to go in the future. So one slide on something we've already done, actually. This, I think, was just due diligence from our part. I explained to you that I computed the phase of the wave function in this geometric optics approximation. This phase has a perturbative expansion in this quantity v over 4gm. We know from Hawking's work that the dominant term is this term here, this log minus 4gm. That's the term that gives the temperature. But we also know that there are corrections because, well, from Hawking's work, you can see that there is really the correction. The correction is just a finite size of the black hole if you want. It's that fact that the event horizon starts 4gm before the radiation falls in. So the correct log really is v minus v plus 4gm. If we expand that in powers of gm over v, this is the correction. So what we did was we went ahead and we computed that correction term. This expansion, well, I already mentioned it, but it's analogous to a post-Minkowski expansion familiar in classical gravitational applications from amplitude. So very familiar sort of a computation. So we just go ahead and we perform the calculation, and this term falls out. Essentially, the finite size effect. The way I think about it is, since this black hole, this event horizon, has a finite size. The black hole isn't just at zero. It's it's got some size, and that's why there's a 4gm here. This particular term is like this finite size effect. Again, that's a little bit connected to classical gravitational physics. There's finite size effects, for black holes, also for neutron stars that people are interested in computing. Usually, there are very high orders of perturbation theory. this one here, rears its head at a lower order of perturbation theory. It is very analogous to the first correction that people care about in these scattering processes. It's relevant for the black hole interaction potential, technically. So it is an interesting quantity. Anyway, so I mean, I guess what I wanted to say is that in terms of due diligence, we felt it was necessary, important to make sure that we had this first correction, so that to validate the methods in a more non-trivial case. So that all works out. It's actually a surprisingly non-trivial calculation. Now, for the future, well, I mean, for me, as a person who works in amplitudes in flat space, I felt it was important, well, I would like to remove the background that we used throughout. So we had this Vadia background. Really, the roles of this background seem to me to be very simple. It doesn't really, I mean, of course, it's important that the black hole forms in this story, but the classical geometry is not very important. And I think it'll be possible to compute this process using flat space amplitudes. What I will do, and we're working on this at the moment, is we're shooting in a coherent state of radiation. So as I had this thin shell of radiation in that Vadia background, now we actually turn on a coherent state of some other scalar field in the far past, and compute essentially just the S matrix, the evolution of this this falling, this coherent state falling in, and forcing it to become a black hole in the future. Now, when I say forcing it, what I really mean is that this coherent state it falls in, we know classically that it's going to form a black hole. If you arrange that the coherent state is thin enough, etc. Some conditions so that this happens, but we know that it's going to form a black hole. I also know from this Vadia metric that to get the Hawking spectrum out, all I need is the transition between flash space and black hole. I don't need any of the details of the actual formation process. So, I guess physically speaking, you're probing, this collapse, in terms of the Hawking calculation, you're probing it with wavelengths which are of order the size of the event horizon or larger. And therefore, the actual microscopic physics of forming the black hole is irrelevant. There's a decoupling. This is like a soft limit. So I don't need to do anything, I believe, in terms of the formation of black hole, other than to introduce some form factor or some, some sort of essentially vertex between the infalling state and the final black hole. I then know it's enough in order to get the scattering, the Hawking spectrum, to scatter a particle off this because of this crossing. So I take one particle, I can scatter it off. I also know it's enough to look at the single graviton exchange because I understand how higher order graviton exchanges are going to iterate and exponentiate. That would be exactly the same as what we've just shown in this work. So in other words, it's just this processes that we need to compute, and we're in the middle of that, and so far it's looking promising. There's another aspect which I think is tantalizing, but which I would like to understand better. And this was something I was looking at while, in the past, but, wasn't able to push it through. And this is, it seems clear from this story that the Hawking particles are produced in a kind of a non-local way. So what I mean by that is, there's essentially this crossing between, this process here where, you're crossing a particle that bends gently along a geodesic, a time-like geodesic. You somehow, and that geodesic is computed by a bunch of diagrams like this, so each graviton gently bends the particle, right? You cross this into the production process. So it seems to me very much like the production process is also quite a gentle thing, that you raise these particles on shell over a spatially extended region. So this is very different from the hard production process of, say, like E plus E minus as a particle collider, for example. That seems very reminiscent of tunneling to me. I don't know if it is, but I think it just seems tantalizing. There's also connections to actions, tunneling, like there should be some imaginary terms. So it's very reminiscent of this work of Tariq and Wilczek, who have a point of view on Hawking radiation related to tunneling. And then just, sort of bookkeeping things, the way we did this exponentiation, I think it could be done more carefully. I think there should be more of a use of stationary phase approximations in the computation. And here I'm thinking of some work of like a group, Gabriele Veneziano, Paolo De Vecchia, Carlo Heisenberg, and Rodolfo Russo in classical gravitational physics and iconal expansion. Finally, I would like to understand radiation reaction. I think that may well be possible using techniques people have already been developing. And maybe in the future, one could hope to begin thinking about the page curve. But that would be, yeah, that's a distant goal right now. Okay, that's all I want to say. Thank you.
Okay, let us all thank Donal. Okay, questions? Okay, I'll start with a slightly naive question. So we speak about radiation reaction. Can we compute the possible Bremsstrahlung, the deceleration radiation in this using these methods?
Yes, yeah, indeed. You know, I mean, I guess when Bremsstrahlung, we're thinking, you know, of low frequency limits of radiation, etc. And that has been very important in our understanding of this classical gravitational waves calculation, or the story. It connects to physics that people care about, the memory effect. And the memory effect essentially is the change, you know, let's say in the E&M, you know, the memory effect just refers to the fact that the Coulomb field in the past and the future are different. That is connected to soft limits of scattering amplitudes. And those soft limits are correctly captured by this formalism. It is actually a pretty cool connection. Yeah, you could certainly fit Bremsstrahlung in here in that context. In gravity, it's of course even more interesting, and there's a very cool connection to some work of Sen on you know, on classical soft theorems. So Sen has these very cool soft theorems. So there's a whole set of connections there, which, you know, I'm not sure, you know, how fully explored they really are. You know, I think there's still questions to be answered in that direction. There has been a calculation of this gravitational waveform in next to leading order fairly recently. You know, I was a little bit involved in, but you know, a whole bunch of scattering amplitudes people like Radu Roiban, Stefano De Angelis, you know, many strong people computed this thing and expanded it in low frequencies and matched onto certain of the terms in Sen's classical soft theorems. That was a very interesting connection. In Hawking radiation, I guess it's a little bit different. I mean, I guess Bremsstrahlung is maybe a little bit different in that context. But I think one thing which for me is, you know, well, just when you mention it, oh, hang on, sorry, I didn't mean to stop that. But yeah, the connection between Hawking radiation and, you know, the sense in which it's kind of a soft limit, I think is very interesting, potentially illuminating. Maybe I can share this again. I think it keeps finishing because it's the last slide.
Okay. Sure. Meanwhile, I think it's Dmitry who wants to ask a question.
Well, I have had a couple of questions. So, well, some of them are very basic. So I'm a bit lost with the setup. So when you discuss this Hawking radiation, you start with A and A daggers, and you have B and B daggers, and you associate both of them with sort of plane wave solutions. They're both IPX exponent of IPX,
Mhm.
right? Why is that you don't have, yeah, here. Why is that for t goes to plus infinity, you don't have like any traces of the background, non-trivial background?
Yeah, I mean, maybe well, yeah, I can see that there could be some confusion here. Yeah. I guess, so yeah, so this is my mistake. So in this slide, what I really have in mind is a very general setup um, for Bogoliubov, where, yeah, so not necessarily. Yeah, so I guess the problem here is I was talking about Hawking radiation, but in this particular setup, I just talked about general Bogoliubovs, where there's just two Hilbert spaces. In Hawking radiation, you might think that there's a simple Hilbert space in the past for free waves, but in the future there's waves that are getting out to sky, but there's also guys that have gone behind the horizon. So in that case, I should really have annihilation operators, ladder operators for the Hilbert space at Scry, the particles that get out, as well as some kind of operators for the states associated with the horizon, like the modes. People sometimes call these the down modes that go down, or the out modes that go down. Sorry, the up and down modes associated with the Hilbert space and the black hole. So I haven't really talked about those because I'm always envisioning a world where I have a detector at Scry. So it's just going to interact with the particles that are getting out. So particles of the B's and the B daggers. So that's what I meant here. So there's a very simple Hilbert space in the past, and then in the future, I'm just going to talk about the particles that get out.
Okay, and also like because it's at Scry, it's very far from black holes, so essentially you can ignore gravitational field, so it's in that limit. So
exactly. So that's why they're free. Yeah.
And can you also explain why one evolves into another with the S matrix, and like what actually contributes to that S matrix? Is it interaction with classical gravitational fields, or what is it?
No, I suppose they have not. Well, of course, you see, the quantum field here is super simple, right? Because okay, you've got the classical gravitational field, and you have, well, maybe it's easier to see it here. Like you have a vertex with one H and two phi's, and that's all you have. So in terms of the Feynman diagrams, the interactions, you can just have chains if you want of phi's. The phi particles with many interactions with the H. That's it.
So this S, which is above the arrow, means interactions with the classical gravitational field.
Yeah. I mean, that's the only interaction in this story.
Okay.
Well, if I were to, so this gets, I think your question is more difficult, when I want to talk about the flat space. So I want to think about the situation where I have a coherent state falling in, and the black hole forms some dynamics, and then I talk about the particles getting out to the future. So there, it's a little bit more tricky, but yeah, that's sort of work in progress. So then all the interactions will just be, gravitons of various kinds, right? It will all just be, all these particles will be interacting gravitationally, but it won't be sort of classical gravity, right? It will be full gravity. Of course, because I know how this particular computation works, I have a sense of what are the diagrams that are relevant when I write everything in terms of flat space field theory.
Okay, thank you.
Yeah.
And concerning the first part, so you discussed the classical limit, and there you had well, I would say quite a complicated construction. You had these wave packets, and I am wondering to what extent it's just the same as just sending momenta to infinity, or it's something more subtle.
Yeah, there's more to it than that. It is important here to put the wave packets in. Now, I didn't really, I mean, I didn't need to say much about them in this construction. I mean, to a extent, this thing here is very general. However, if I want to apply this to classical gravitational backgrounds, then it's important that to a classical scattering situation, then it's important that the details of the wave packet cancel out. I mean, obviously, a classical situation, it doesn't care about the wave packet of a particle, right? So, and there's a mechanism whereby that happens, which involves essentially some hierarchy of momenta. So, there's some momenta in the problem which are big and some momenta which are small. So the momenta associated with the mass of particle is basically big. It's got the mass of the particle in it. The momenta of gravitons small. You have to perform some expansions of these things. And when you do that, you can indeed remove the dependence on the wave packets. I mean, they essentially just localize some momentum integral to the peak of the Gaussians, and then they fall out of the problem. So they play a role, but in the end of the day, they go away. It's a little like textbook discussions of the formula for the cross section, d sigma d omega in a scattering event. Obviously we write that as some integral over the square of an amplitude, but at least in the middle of that derivation, you'll introduce wave packets. It gets complicated. It gets a bit technical, But at the end of the day, the expression is simple.
But
so you don't care about diffractive physics, obviously.
Yeah. And the eventual formula is not just sending p to infinity. Once you will do this.
No. You essentially, you see, classically speaking, you want the amount of particles to be a mass times the classical velocity. There's going to be an mv. But there will be a strong ratio between that momentum and the momentum of gravitons, because classically gravitons don't have a momentum, they have a wave number. So there'll be a h bar between these things, and yeah. So there's some expansion that one does. It's more like a soft expansion. So there's a connection to iconal physics for that reason.
Okay, and the last thing concerning, well, you mentioned briefly in the second part concerning IR divergences, but do you have like any IR divergences here with the waveforms?
Yes. Yeah. Good question. Yeah, the waveform is IR divergent. Yeah.
And is it consistent with like typical computations which are not relying on amplitudes? Do you have them there as well?
Yes. Yeah. It's a physical divergence. Yeah, it's essentially the divergence. Is associated with the long time of flight between the source and the event, and also the time of flight of the particles as they come in. So to the extent that you take all of these distances to be infinite, there's really a divergence, but divergence is cut off by finite size of propagation, physically speaking.
And physically, what's the meaning of this divergence? The gravitational wave energy emitted is infinite, or what is it?
No. So it exponentiates into a phase, and it just corresponds to a divergent shift in the origin of time, of the retarded time. There will be some retarded time at a detector, some retarded time u, and that retarded time u has an additive IR divergence. So you can just absorb it into a time shift, and that's what people do. You just absorb it into a time shift. There is a connection here to another interesting topic, which is BMS frame, like the large gauge transformations. Large gauge transformations act on these waveforms, and they act precisely as a shift of the retarded time. Anyway, I don't know if BMS is a topic that interests you. It's something that's arisen in this context. I think it's very interesting. A connection between infrared physics of scattering amplitudes and large gauge symmetries of general relativity.
Okay, thank you.
Thank you.
Yeah, I have one last question about the role of the asymptotic. So what happens if we instead doing de Sitter?
Okay, yeah, interesting. Yeah, I mean, at one level, that's a tough question, because when we're talking about scattering amplitudes, we really do have in mind that the boundary of space-time is asymptotically Minkowski, and so that we can, so that we can set up a standard, in-out scattering process without, kind of cosmological horizons. In terms of the gravitational waveform, there is a pragmatic interest in de Sitter, because obviously we have an accelerated phase of expansion in our universe. Also, in the future, people are talking about gravitational observatories that will detect black holes over cosmological distances, so the redshift will be an effect. So now I'm not to my knowledge, there's no literature using scattering amplitudes in that context, but I think it should be possible to treat the redshift here as being a perturbation, because we're just to the extent that we just about see things with non-zero redshifts, they can't dramatically change the waveform. So it should be possible to take into account that stretching of the waveform over the cosmological distance using some fairly simple algorithm. It's not going to totally destroy the setup, but so it would be interesting to do that. I sort of think it would be interesting, just to, as a pragmatic question, can we take into account, some deviation of the redshift from, and maybe you could then try to build on that to think about, what is the generalization of these kind of amplitudes in a de Sitter context that actually would make sense. I mean, they won't be quite, amplitudes in the same sense, but there are people, I'm thinking of Guy Pimentel, who are thinking about S matrices in de Sitter space, or more interesting space times. And I guess what I understand from that discussion is that maybe there's more than one definition of S matrix that's useful. There might be a specific definition that's useful in this context. But yeah, I mean, that's something that I think is completely open. Actually, it's an interesting topic.
I see. Okay, well, that's definitely very interesting. And of course, I want to. Okay, so I don't have any questions, and I don't think other participants have any. Yeah. Okay. So in this case, I would like to thank you for your talk, Donal.
Well, thank you. Thanks for the invitation, and yeah, pleasure to get the opportunity to present my work to you.
Yes, we were very happy to hear you. And okay, well, see you. Well, hopefully
again.
Time.
Thank you.
Yes. Bye, everybody. Bye.
Bye.
Thanks for listening.